Yeah, so we're really excited to have Mario here today from Yale University. Mario Belledonne previously worked with Josh Tenenbaum at MIT from 2016 to 2019. And currently he's doing a PhD at Yale with Ilker Yildirim on their psychology program. And there he works on computational models of high-level mental processes in domains of intuitive physics, scene perceptions, and more recently, Atari-style games. So yeah, Mario, take it away.
Great. Thanks, Augustine. And thank you all for hosting me today. I'm really excited to present this work to a computer science audience. Alrighty, just as a quick check, can everyone hear me okay and are the slides going through?
Yes.
Okay, excellent. Thank you. Hello, everyone. I'm a third-year graduate student in the psychology department at Yale University, working with Professor Ilker Yildirim in the Cognitive and Neural Computation Lab. Today, I'm going to present some of my work from the past 2 years about a new way to think about the nature of attention in perception and cognition. This is based on a new computational architecture that formalizes how goals should drive the formation of percepts based on multi-granular representations and adaptive computation. Let's start with the question: what is attention? As many of you are probably aware, machine learning and artificial intelligence, ideas around attention have manifested in recent work on transformers that learn mappings of features across series of symbols without relying on recurrence or convolution, especially in the domain of language models. But today, I'll talk about a very different perspective on attention. The concept of attention has many different meanings in psychology and neuroscience, but here is perhaps the quintessential example of what I call goal-directed high-level attention. I'm sure many of you, if not all, have seen this invisible gorilla demo, but I want you to remember how astonishing it was to realize that you missed this guy coming across the entire scene in a ridiculous gorilla suit. Well, this demo was made in the late 90s or early 2000s, and despite the passing of 2 decades, we still don't understand how we can miss such a salient event taking place right in front of our eyes. While it is possible to dismiss this phenomena as a quirk of the human mind, I argue that this ability to selectively process the world in a goal-directed manner is vital to understand human proficiency in interacting with complex and dynamic environments. And that's the kind of attention today we'll focus on and capture its computational principles in this talk: the nature of high-level attention, the goal-driven processing of sense inputs in terms of selective and multi-granular world models. What do I mean by that? We can find signatures of this kind of experience almost everywhere in our daily lives. For example, take many modern or classic video games. Humans find these games fun, in part because we see common elements between our real world and these games in terms of objects, agents, and places. However, this representational richness is accompanied by a representational depth, a sort of coarse-to-fine hierarchy. Here, when playing video games like Phoenix, a title from the Atari console, the mind needs to carve out only a small fraction of the sense input and model it in detail. Here, multi-granularity comes to life. Things can be individuated like objects, as I'm showing, but can also be blurry amalgams like clouds of objects or ensembles. Much of this representational topology, including its richness and depth, is determined by our implicit or explicit goals, or what we need to know for goal-directed action. Similar experiences are operational across different video games or in the real life. During driving, you represent each element in the scene, including pedestrians and the traffic, in a multi-granular hierarchy, according to their relevance for safely driving throughout the roundabout. Despite decades of progress across multiple computational traditions, we still lack a basic understanding of the computational principles behind such goal-directed, high-level attention. And now I'm going to tell you about 2 of those approaches. The first approach involves analysis by synthesis, where perception performs inference to the best explanation of sense data by inverting its underlying causal structure. This approach has been increasingly influential in the study of human physical scene understanding and object-level perception, with representational targets such as objects and agents, but these generative models do not support representational depth. Most traditional approaches in analysis by synthesis attempt to simulate all aspects of the scene in implausible detail, or rely on haphazard rules to reduce complexity. There is a fundamental challenge here, in that within perception, there are no visual cues to the right level of granularity. Without a principled mechanism for selective processing, such as goal-driven attention, most of the posterior approximated in such models can be useless, yet accrue at incredible cost. The second approach involves modern machine learning, which had revolutionary success in recent years through deep neural networks. These include deep convolutional neural networks and models such as Google's DQN and Mu0 that learn unstructured models over the world in order to support effective planning. While this line of work appreciates the idea of goal-driven processing, they rigidly integrate a single goal. In addition, the unstructured embedding of representations as static vectors precludes rich and flexible beliefs. Thus, unlike a human that could pivot from playing one game mode to another, these models require millions of steps per scenario. However, this talk isn't about reinforcement learning, or learning to play, but rather a broader set of mental faculties that ultimately enable robust as well as rapid learning. This talk is about seeing effectively. In an attempt to address these limitations of previous approaches, I've been building a new computational theory that formalizes the perception to cognition interface, the adaptive computation architecture of attention, that marries and extends some of the two foundational theories in psychology: Ulrich Neisser's cognitive psychology, where goals drive mental processing, and David Marr's vision, that we see in terms of rich representations like objects. This general computation architecture provides a concrete manifestation of a long postulate interface between what we see and what we think, by formalizing for the first time how attention guides goal-driven processes in perception. This talk will consist of two main parts. In the first part, our architecture illustrates how goal-driven selectivity over coarse-defined multi-granular representations can reveal something about the basic nature of human scene perception. As a technical overview, we'll draw on multiple formalisms, including modern probabilistic programming, multi-granular state spaces, multi-granular planners, sensitivity analysis from information theory, and adaptive computation. In this talk, we'll see an example of this architecture in scene perception, as well as in part 2, a domain that emphasizes dynamic attention, multiple object tracking. I hope you can appreciate the homology between these two instantiations of the architecture. The starting point for us in this project focuses on arguably the most profound finding in modern vision science, that scene perception yields incredibly sparse and selective content. We've already encountered an example of sparse scene representations, but here we are interested in scenes as places. And if scene percepts are sparse, what do we really see in a scene like this one? Here, our percept of this church contains several kinds of representations: the overall boundary of the environment, and set of objects and agents of interest, and how we can get to them. Importantly, not all scene geometry is represented equally. For example, it is unlikely that each pew is distinctly encoded in our scene percept. Or consider this outdoor scene on a hiking trail. In a sense, there's so much to see in this complex visual environment: the rocks, the trees, the scattering of the light, but at the same time as one is navigating it, these things don't enter our percepts in the same way. For example, do you see this patch of rocks on the left in the same way that you see these patch of rocks on the right? Each of these patches are similar in terms of their texture and distance to the observer, yet we experience those patches differently. They matter to a different extent in terms of the path that likely take you forward on this trail, and perhaps this context drives the perceptual mechanisms to selectively process one patch over the other. These examples highlight how scene perception is highly selective. Many changes in a scene can go unnoticed if those changes occur during a blink or a saccade, but at the same time, scene perception supports ecologically critical functions such as navigation, which requires a detailed analysis of scene geometry, including paths to points of interest and obstacles along the way. It is perhaps not surprising that neither analysis by synthesis nor neural networks trained to classify images can explain both of these seemingly paradoxical aspects of scene perception. We make progress in this direction starting with synthetic yet realistic indoor settings, with visible exits and obstacles. And again, our approach is based on a marriage of these traditions. Similar to analysis by synthesis, we formalize perception as a form of online inference, but with the critical difference that the generative model represents the scene with multi-granular geometry representations, and that the estimation of this posterior is driven by an implicit goal to navigate the room, getting from the entrance to the exit. Let's begin with perception. At a high level, the perception module applies an efficient population MCMC procedure to a multi-granular coarse-defined generative model. We'll discuss more about the efficiency and population features of the inference procedure towards the end of this section, but for now, let's focus on what we mean by multi-granularity in the domain of scene geometry. Here, generative models transform input images into multi-granular scene geometry. Multi-granularity is defined as a course-defined encodings of the geometry where beliefs are described by probabilities of obstacles residing on points in the room. We operationalize multi-granularity by evenly dividing space into what we call spatial trackers that can independently describe the respective regions in terms of Bernoulli latents at different levels of granularity. Spatial trackers behave similar to quad trees or other course-defined structures, where at the coarsest level, the entire subspace of a tracker is defined by one latent. Intermediate level trackers divide the underlying space into respective latent dimensions. And finally, the most refined trackers define the upper bound for spatial resolution of the model, with each latent in the tracker corresponding to a point in the scene. Here, you can see that across trackers, multiple levels of granularity are present simultaneously for this particular hypothesis. Next, we're going to look at one of the ways multi-granularity enables efficient inference. Likelihood. Multi-granular tracker representations form a principled link between representational resolution and uncertainty in predictions. Here, the likelihood over an image is derived as an empirical distribution arising from multiple instantiations sampled from the Bernoulli weights across trackers. Using a differentiable renderer that supports batch processing, the generative model is able to render all instances in parallel and collectively define the mean and variance of a multivariate normal distribution over the image space. Just as tracker resolution can vary from one region to the next, so can the variance term of the likelihood. Now that we have given an overview of multi-granular perception, we can move on to the second module of our framework that describes how an observer can plan over multi-granular geometry. For the goal module, we propose that humans automatically process scene representations to serve as a set of implicit goals, such as navigating through a room. We represent the knowledge extracted from scene geometry as navigational affordances, or the probability that a point lies along the shortest path from the current location of the observer, here in green, to the exit, in red. In this work, we assume that the observer can accurately encode the entrance and exit locations. As with likelihood, the model leverages multi-granular structure of scene geometry to efficiently compute navigational affordances using the A-star algorithm. Similar to quad trees, the collection of trackers dramatically reduce the number of vertices in the scene graph. This is supported by the structure of each tracker, where each tracker latent describes a single vertex in a multi-resolution path graph. The distance between vertices is a function of coarseness, and the cost of traveling through a vertex is proportional to the confidence of obstacle occupancy. Here I'm showing an example of a tracker in a rather large scene, where in the top row, A-star finds a path through a highly granular representation of geometry, on average taking about 3.8 milliseconds. With multi-granular representations, a very similar path is recovered with a fraction of computational and representational resources. But how would we refine what level of granularity each tracker should occupy? Again, there are no inherent visual cues for this. Instead, the adaptive computation architecture relies on attention modules to quantify how goal-relevant each tracker is to navigation via sensitivity analysis. On the left is the ground truth of scene geometry, and this is the inferred state at this point in the chain. Remember that these trackers have evenly divided the scene and guide inference about the granularity of geometry. During inference, proposals to individual trackers can lead to large or small changes in navigational affordance, corresponding to high and low changes, respectively. To quantify the resulting difference in navigational affordances, we use the cost of the unbalanced optimal transport plan approximated using the Sinkhorn algorithm. Here, for example, sensitivity analysis reveals that intuitively, trackers along the general path to the exit are significantly more goal-relevant than other trackers, and thus should receive more attention in the form of Bayesian belief updates. This is scheduled by the final module in our framework that selectively attends to each tracker via adaptive computation. Here, the goal-driven hypotheses, or sensitivity weights for each tracker, form the basis of a population MCMC procedure, with such weights modulating convergence rates across goal-relevant trackers by selectively applying local MCMC kernels. Here, the MCMC kernel allocates computational and representational resources in the form of two flavors of Bayesian belief updates. The first flavor describes the allocation of representational resources to form alternative hypotheses over tracker granularity. We evaluate these hypotheses using involutive MCMC moves between finer or coarser granularities. The involution kernel is critical to incorporating the change of variables across levels of resolution. The second flavor describes the allocation of computing cycles to guide a random walk over obstacle probabilities within a given resolution level. These follow more traditional MCMC methods, but in our current implementation, we combine both involution and random walk into the same MCMC kernel, such that both flavors are considered in tandem. Now that we have discussed the population aspect of the inference procedure, let's briefly go over what makes it efficient. It's well known that inverse graphics is a notoriously difficult inverse problem. Inspired by recent work building inference networks, we incorporated a bottom-up module, taking the form of a variational autoencoder to efficiently initialize our MCMC chain as a data-driven proposal. Here, we trained the autoencoder to reconstruct scene images and used its learned latent space to also decode the scene state with a second decoder. As you can see, the resulting proposals are far from 100% accurate. They are, in fact, in some ways impoverished. Yet these proposals provide a reasonable starting point for inference that would otherwise be computationally difficult to achieve with purely traditional Monte Carlo methods. Thus, this system provides an example of how modern machine learning approaches can seamlessly interface with inference over complex generative models containing multi-granular representations. This framework predicts that selective processing over multi-granular geometry representations in scene perception arises from automatic or spontaneous computation of navigational affordances during passive viewing. We're going to test this framework in a psychophysics experiment that provides us with an objective measure of human performance. Here, we implement a change detection paradigm to evaluate the automaticity of navigational affordances in scene perception. If scene geometry is selectively processed in the service of efficiently computing navigational affordances, then humans should be more readily able to detect changes in geometry that result in a difference in the shortest path relative to changes in geometry that do not impact those shortest paths. Here, I'm showing an example of the same shortest path trial, where the change in geometry highlighted in yellow does not change the shortest path. To address potential confounds with changes in geometry leading to salient visual cues that might bias hit rate, all we do is move the door, such that the change in geometry now affects the shortest path while keeping all changes in geometry constant. Let's take a bird's eye view of these two trials we just looked at to better see the shortest paths. I am again highlighting the change in geometry in yellow, and I'm also showing the aggregate of all shortest paths using this green color. You can see that this is the same path pair where the change in geometry does not impact navigational affordances. Contrast this to a different path example, where we apply the exact same modification to geometry, but this time it impacts navigational affordances. We predict that people will more readily detect the same change in geometry when it matters for navigation. We generated a series of trials with controls, some that had changes in geometry that did not result in the shortest path, and some that had a change in geometry that resulted in the shortest path. And as we predicted, we found that the number of changes successfully detected are significantly higher when the changes where the change in geometry accompanied a difference in shortest path. Now that we've reported some of the evidence suggesting the presence of selective processing in scene perception, let's turn to the model to explain how much differences in paths increased in hit rate within a scene as a function of attention, or sensitivity predicted by our model. Here, we see that our model captures much of the explainable variance in the data. This R-squared approaches the consistency between responses of our subjects. While the design of stimuli pairs between same and different path trials already minimize the pixel level differences, we can more directly test whether residual changes in pixels predict behavior. Consistent with our predictions, these pixel level changes are unrelated to behavior. So far, I have shown through an instance of the adaptive computation architecture how we can understand human scene perception as guided by automatic computation of navigational affordances. And importantly, this provides a general computation architecture for this kind of interface that has long been elusive between perception and cognition, by formalizing for the first time something about high-level attention, how implicit or explicit goals should drive the formation of percepts. And functionally, this can scale to rich structured world models over complex environments by bringing together adaptive computation and selective multi-granular representation. Returning for a moment to illustrations presented earlier, there are a few critical elements not captured in the previous domain of scene perception. Dynamics. Human perception and attention is full of dynamics. We shift our attention across objects and moments in time, as well as from one goal to the next. In this part of the talk, we'll develop an instance of the adaptive computation architecture in the context of multiple object tracking using a simple display such as this. The task is straightforward. Initially, you observe a scene where a subset of items are indicated as targets, then all objects start moving for a period of time, and finally, once all objects come to rest, participants might identify the targets. These displays look deceptively simple, but this paradigm has been the topic of hundreds of papers in psychology and is a paradigmatic example of dynamic object-level attention. But this paradigm is even richer than typically acknowledged, with hundreds of papers and existing computational models reducing each trial to a single value, overall tracking performance. But these works have never been able to capture the reality that each trial presents an experiment unto itself. For example, some trials are easy, requiring very little effort. And some others are hard, where sustained attention manifests with exertion. And throughout each trial, there's a dynamic ebb and flow of attention. Our ambition here is to capture this experience in its totality, in its ebb and flow. And while this takes some technical sophistication, we believe that putting all this hard work up front will pay off, and that our model can generalize to more complex displays and dynamics readily. Like before, the first step involves a perception module that performs online inference, in this case in the form of a particle filter, turning incoming displays into dynamic scene representations consisting of persistent trackers that are expensive yet expressive, and ensembles with cheap and impersistent representations. While not as expressive in terms of granularity as spatial trackers from scene perception, this combination of individual object trackers and uniform ensembles provide a minimal interface for attention to choose what objects are important to represent. In future work that we will visit in the last part of this talk, we are exploring recent advances in normalizing flows that we hope enable more informative intermediate granularities. The likelihood over a generative model draws from two inspirations: literature on human vision, as well as ideas from stochastic geometry. The inputs to this model, the observations, are segmented motion masks, which are image computable using simple motion detectors. Given that nature does not provide a veritable pairing between object representations and masks, we define the likelihood of a set of observed masks X given a set of mental representations E as a random finite set. The support of a set of explanations, that a set of explanation has over a set of observations is the cumulative support for each possible partition F between explanation and observation elements. Valid partitions under this distribution are those in which each observation must be explained, and it is possible to associate multiple observations to the same explanation, as shown below. Here, we see an important consequence of multi-granularity between trackers and ensembles. Each tracker with persistent identity and detailed trajectories forms a Bernoulli element that only supports at most one assignment per partition, whereas the ensemble, having no spatial information or persistence, can support the full range of assignments by taking the form of a Poisson point process, as highlighted here. Next, this framework specifies the observer's goal, or what the agent needs to know about the world in order to interact effectively. For MOT, we define the goal as set tracking. Instead of need to know the precise identity of each tracked object, the observer only needs to delineate between the target set and distractor set. The language of random finite sets identifies this measure as the probability that a subset of observations is associated with any tracker. This can be estimated as a marginal over partitions. Note that such measures would not be principled under heuristic functions for likelihood, such as the Hungarian algorithm. Step 3 of 4 in this framework is to implement task-driven hypotheses about the goal relevance of each object representation. The key to this step is to quantify how much goal-driven beliefs, that is, the target set in MOT, change as a function of incremental improvements to object representations. On the left is a collection of observations, and this is the inferred scene state at that instant. Remember that trackers structure the position and prediction as well as action over target status. We will use sensitivity analysis to quantify how much the target set would change as a result of incremental improvements on a given tracker. By perturbing object representations as one would during rejuvenation, the framework can quantify whether changes to a given representation can lead to large or small changes in the target set. Through sensitivity analysis, we again approximate this change as the cost of unbalanced the unbalanced optimal transport plan between the original and alternative hypotheses using the Sinkhorn algorithm. Here, for example, sensitivity analysis reveals that the purple tracker is significantly more goal-relevant than other trackers at this moment. And this is what's going to implement our model's notion of moment-by-moment attention. The final step in our framework is an adaptive computation module that uses the results from sensitivity analysis to drive the convergence of approximate inference towards the most goal-relevant representations. And the distribution of allocated cycles ebbs and flows as the scene unfolds. Here, you can see the model in action. Those red rings that appear momentarily indicate the allocation of computing cycles, with their intensity proportional to the amount of cycles. Intuitively, attending more to those trackers at risk of being confused with distractors. So what do we get from this framework? We have a fine-grained account of dynamic attention that we will evaluate on human tracking data from 2 high-resolution experiments. In our first experiment, we're going to measure both tracking performance and subjective effort experienced on each trial. We predict that the amount of effort experienced during a trial will correspond to the cumulative amount of cycles allocated in the model for that trial. And that's exactly what we find. First, this model reliably predicts human tracking performance. And second, it also predicts participants' subjective effort ratings, even when controlling for shared variance with human accuracy. In the second experiment, we're going to add a measure of attention that captures the moment-by-moment ebb and flow of selection within each trial. During the tracking phase, subjects had to detect several subtle probes that appeared momentarily on objects, with the idea that for a given moment, more attention to an object will lead to increased hit rate. We model this distribution of attention as a centroid that arises from the average location across tracked targets, weighed relative to their allocated cycles. In doing so, we will control for more traditional generic spatial factors, including the geometric centroid. Not only does the attention centroid explain a large portion of variance in subject hit rate, but the attention centroid is able to explain hit rate even after removing contribution of geometric centroid, whereas this is not the case in reverse. Importantly, this effect survives a replication in a new set of probe placements on a separate experiment. Here, through the adaptive computation architecture, we reverse engineered the dynamics of high-level attention in humans predicting objective measure of human behavior at sub-second resolution without domain-specific assumptions that could readily generalize to more complex dynamic settings. And importantly, these results establish the generality of this computational architecture that I have introduced by formalizing this perception to cognition interface in terms of the mechanisms in which goals drive the formation of percepts over multi-granular substrates. One of the most personally exciting aspects of our work is the flow of cognitive and engineering milestones. While there are many active directions, I'd like to share some that summarize our enthusiasm. We are particularly excited about exploring richer and deeper forms of granularity. As you may have noticed for both objects and places, the ladder of granularity shared a similar structure. There was a split process that defined how representations could increase in granularity and a merge process going in the other direction. We believe that we need to innovate, that innovations from machine learning will help us expand the rungs of the representational ladder. For example, normalizing flows that can natively support the interface required by involution MCMC. With this tool in hand, one of the first domains we wish to explore is Phoenix, with its rich blends of dynamic attention and goal-directed action. Here, we hope that normalizing flows can provide us with a richer intermediate ensemble representations, allowing the agent to use multi-granular planners over an informed subset of the scene. In a similar vein, we hope to integrate what we learned from scene perception and multiple object tracking by exploring settings such as Doom and other first-person games that include both static and dynamic scene elements. As you can see here, the human player easily dodges multiple attacking enemies while searching for a static object of interest, some sort of switch. But importantly, I hope this talk has inspired you to think about what it means to see in the real world. For the mind to turn a stream of sensory wiggles into objects, places, agents, and events. With that, I'd like to thank my collaborators on these projects, the rest of the cognitive, especially the Yale Computing Center, as well as GEN, which is the probabilistic language that we use throughout the talk, the rest of the cognitive and neural computation lab, as well as the broader Yale psychology community. And of course, thank you, the audience, for your attention.
Thank you. That was really interesting, Mario. So yeah, we've got time for questions now. I guess I can start the questions. Can you hear me all right?
Sorry, I'm back over here. I couldn't unmute myself. Sorry, if anybody has questions, if they want to put it up in the chat.
Yeah.
Should we wait for that?
Yeah, or I guess they can also just ask whatever they're more comfortable with. But I have one question maybe to start off.
Please.
So in the sort of navigational affordances experiment, is the goal of navigation specified beforehand? Is that like a...
No. So importantly in this experiment, the idea here is that there are these notions of implicit goals that we just inherently, the mind wants to kind of just inherently extract certain information that's ecologically relevant. So in this case, we don't tell the subjects anything. We just basically say, do a change detection test. You're going to see two images. Click if you think they're different or the same. So, you know, one image shows for 500 milliseconds, then there's this blank screen, and then there's another image for 500 milliseconds. And they're supposed to press one key if they think it's the same, and the other key that's safe if it's different. So the main point here is we will change something about the scene, and that something may be along a path, something that you should be attending to, or may not be along a path, something that you shouldn't be attending to. And what we find is that if it's along a path, that people are more readily able to detect it, even though, in a sense, there's no visual feature that could kind of indicate that from a kind of a pixel level wise analysis.
Mm-hmm. So if I understand correctly, without telling it the goal of navigation, it learns what to attend to.
Oh, I see. Okay, so there's two things here. Yes, there is the model, and then there's the humans. So the humans, we don't tell them, so we assume that they have the goal. And the model itself explicitly does have a goal.
Okay.
So it is inherently extracting navigational affordances. So the idea is, you know, you have this multi-granular posterior. It's really big, like for a posterior, because it's not only just like what's the best explanation of the world, but across levels of representation, what's the best representation of the world. But the idea is that most of those axes in the posterior, going from your base distribution to the true posterior, are kind of irrelevant. You can converge to 90% or 80% of the total posterior, but basically have gotten to peak performance. So the idea is, okay, we assume that humans have this implicit goal of navigation. There are some interesting work in developmental psychology that kind of, you know, this comes from things like, you know, active learning and exploration and curiosity. All those lines of work kind of stem in here, where somehow humans kind of have this impulse to explore. In order to explore, you have to kind of have a navigational plan of some sorts. So the idea is like, yes, we explicitly give navigational affordances to this model. The fun thing about this kind of architecture is that, you know, you could define a learning loop. You could also define multiple goals. So you can have navigation, you can have search, you can have avoidance, you can have chasing. Like all of those things can kind of be stacked onto here. There is a question of exactly how you learn those and what combinations are present when. So where did the goals come from? That's a very deep question in cognitive science. But
yeah, I guess that's kind of what I was thinking. You know, like in your Phoenix game, how if you're not quite sure what, you know, when you initially play the game, maybe you don't know that you need to shoot the monsters or the spaceships or whatever. So how do you know what to attend to if you don't understand the goal yet? I guess that's kind of...
Right. That's actually an excellent question, and I think that in practice you can't, unless you actually like. So the idea here is like we have to start from somewhere. So just pragmatically, we're going to start with, you know, kind of like a simple MDP process that has some relatively short horizon time, but the state is a world model containing things like objects and like some sort of primitive engine, causal engine. And yes, it is. I think it's a very interesting question how you know, can, you know, in a sense, like we don't, like there are some rules that we need to learn in some games, but a lot of games we can play, especially if they're well designed, we can play without really learning too many rules. I mean,
Hmm.
better rules come into play as we practice more and more. But the basic notion of I don't want to get hit by a missile, and these things are not the same thing as me, so perhaps I'm going to be aggressive towards them. Those are kind of inherent human characteristics. So
cool. And do you see these? I mean, I know that in robotics and stuff, there's kind of ideas that certain affordances or certain objects suggest certain actions. Like a mug suggests that you should pick it up, kind of thing. Do you see this model kind of translating to more higher level tasks than navigation? Things like, say, grasping or
yeah. Yes, it kind of like that. That's kind of a bit of a more unexplored area in cognitive science, because there has to be, like, we talk about a lot of in our generative models. A lot of this talk focuses on perception, obviously. So the generative model, the ladder of causation, is really just about a little bit of dynamics in the world, graphics, and then your observation space. But in cognition, there's this whole other realm of what kind of state do I want to get to? What things do I want, right? And but in terms of things like grasping, there's this idea that, like, as long as you can define why you want to grasp something, like some impulse to grasp something, maybe I'm thirsty, maybe I want to use this to open a door, whatever. Like there is a sense in which, like, if you were, for example, one kind of the extensions we want to do, there's some interesting work both in AI and stuff on kind of indoor scene navigation, 3D scene navigation on like scene graphs and things like that. One of the things that we'd like to explore here is the idea of, like, okay, so one step is just navigation, but the other thing is search. And search gets much more fun when you think of things like containment relationships. And that's where, for example, looking for a handle, something that you can grasp, becomes much more important. And of course, there is another side to attention here that I haven't discussed. I've only discussed goal-driven attention primarily because it's just really not explored in our field. But there's another one that's kind of, especially in neuroscience, talked a lot, called salience, or bottom-up attention, which can be seen as like an amortization of this. The idea is that there's you want to avoid large felines usually in nature, or you want to avoid snakes. So there, you can amortize a mapping of features to a higher resolution representation. So if you see some squiggly thing on the ground, you might be wrong some of the time, but you're ecologically well off if you just inherently grabs your attention, and you inherently see that as a snake, as a high detailed representation, rather than just like shadow or something. So there's a sense in which, once you learn that handles are important because they can open containment things that might show you what you're looking for, there might be a sense in which you learn in an offline sense features like handles. You start becoming very attentive to these relatively artificial, easy to detect horizontal and vertical features that make up a handle.
7 films per week.
Sorry.
Sorry, does anybody have any questions?
Yes, Dennis asked a quick question about paper. Yes, this stuff is a little bit delayed. There's been a few conference talks. I'm happy to send those out on this. We've had a conference talk at CogSci and VSS for the multiple object tracking stuff, and we've had another talk at CogSci on the scene stuff most recently. We hope that both of those manuscripts will be out really soon, hopefully in the next month or so, at least on archive. Unfortunately, those talks geared for more a CogSci audience or psychology audience probably won't have more technical detail than you've seen here. And of course, all the code will be published at that time. It's mainly in Julia, which hosts the Gen package, which is our probabilistic computing language. But of course, we use PyTorch modules here and there and stuff like that.
Cool. I have another question, so I'm kind of hogging the questions, but so you talk a lot about efficiencies, and it kind of makes me think, one of the big problems in reinforcement learning, especially with high dimensional things like Atari, is that they're horribly sample inefficient. So you need hundreds of, in some cases, hundreds of millions of frames to learn to play a game.
Right.
So I'm wondering if your work has any applications, talk about different coarser levels of representations and things like that. I'm wondering, I've thought about how that could potentially help with sample efficiency? Are those kind of efficiencies you mean, or?
Yeah, for sure. There's and that's kind of a little bit illustrated here, although perhaps not very saliently. There's the idea that, like, for example, in the navigation stuff, the idea of having a sparse scene graph is not novel. It's been around for a while. The question is, like, what sparsity do you use, and is one level of sparsity appropriate for all Apple applications? So, like, obviously for humans, it tends to ebb and flow. It tends to switch a lot, both within a setting and across settings. So there is a sense here in which, and we have some kind of higher level plans for this, or like sketches, but we might touch upon later. But there's a general sense in which, you can have this like sleep-wake cycle with these types of approaches, where you can imagine having a perception trial during wake time, and just imagine for some reason you save kind of the set of observations, your set of beliefs, your approximate posterior, your actions, your expected utility and your actual utility, expected performance and actual performance. And what you can do is kind of, there's things like inductive logic programs that you can have a probabilistic spin on that can be core modules of the generative model, such that you're like, okay, I had this representation for an ensemble and it got me this performance. What I mean by performance is it literally took these amount of, MCMC kernel moves, these number of bits, this amount of memory capacity, whatever, to get to this level of accuracy or reward or something like that. You could counterfactually change those within that setting. And most of these inference procedures, I didn't talk about it, but they're relatively fast. I mean, with these types of multi-granular representations for MOT, we can easily do it in like 20 particles. It's about, it's close to real time. I'm sure, I'm not a hardcore CS engineer, so I'm sure someone with more optimization chops could probably get it to be close to real time. But the idea is if you amortize, if you kind of have, one of the things we're excited about normalizing flows is the ability to say, okay, I don't need to, as an engineer, describe random variables in closed form. I don't need to say, here's a Poisson point process, here is a Gaussian or whatever. Things like normalizing flows and other variational approaches should, like, you can imagine a framework where you're like, okay, I had this ensemble representation. It's defined by this this neural network with these weights, right? What happens, like, if I slightly perturb either my goal specification, my object representation specification, such that I can achieve one of two things: either lower resource cost to approximate a representation, or just higher accuracy. So the nice thing about thinking about goal-directed perception is it gives you kind of a relatively, of course, there's leeway in how you formalize it or quantify it, but it gives you a formalization for how to quantify efficiency in general, at least for perception and action. So like, one of the things that we're happy about, like, think about Doom is, like, you can imagine that there's a switch that this player is trying to get to, and he's kind of looking around the room for it. Or I think first what happens is he first sees that the room is closed, so he's trying to get to the next part. There's some enemies that he has some representation of. I doubt that they're necessarily very high resolution, but they're high enough such that he recognizes that they're enemies and he moves away. So you can kind of counterfactually compare what the trade-off would have been to represent those two individuals at a higher level of resolution, so more, like, less variance in your prediction, right? But it would have been more cost to approximate that, both in terms of inference because of the number of latents, and in terms of planning because of the complexity of those representations. Mm-hmm. And you can see, like, okay, well, actually, now that I've encountered this type of enemy, these are like impy type demon things, I have, like, a pretty good idea, like, in this setting, like, of I guess Doom, I have a lot of information to kind of define how much of the representational granularity ladder I need to play this game effectively. And instead of exploring the entire ladder every single time I play this game, I can really just cut it off at particular chunks. So there is a sense in which you can have a relatively, like, things like involution MCMC give you, like, a huge space of representations to work with. And there definitely seems to be a case in which humans do learn, not necessarily to attend, but what space of that ladder is important for a context, for a specific setting. So there's a sense in which you should be able to learn something over that framework.
Cool. That's really interesting. Thank you.